The Baeyer Villiger oxidation reaction can start off with two different starting reagents. It can start off with either a ketone or an aldehyde. This ketone or aldehyde is treated with an R group that's directly conjugated to CO3H. Now, R group just means anything that is in hydrogen. And again, this is called a peroxy acid. Now, a lot of the times in lab, this peroxy acid will be given to us using a named reagent. This named reagent is called MCPBA. MCPBA is essentially an alcohol that's connected to an ester that has a chlorine group attached to it. And the full name for this is metachloroperoxybenzoic acid. Now, for this example, let's just use an R group as our substituent on the peroxy acid. So, let's do the actual mechanism now with a random ketone. Let's use this as our starting ketone. And let's treat this with our peroxy acid. And let's do a methoxy group. So, the first step is this oxygen attacks the double bond and makes this into an oxyanion. Now this results in this structure where we have a plus charge and a negative charge. Obviously, an excess in charges is already a problem. This renders our molecule unstable, so we want to get rid of this as soon as possible. A plausible step would be doing a proton transfer on the alcohol and the oxyanion. However, this is a favorable step, but it's not what we're looking for within the Baeyer Villiger oxidation. And again, in chemistry, everything is in equilibrium. Because everything is in equilibrium, of course this proton transfer does occur in lab, but for the sake of the Baeyer Villiger oxidation, when we treat this with the peroxy acid, the final product is the more favorable resulting product. Rather, if we do this proton transfer step, it would lead to something called a tautomerization, where this alcohol will tautomerize into a ketone, which would ultimately cause this to somehow be a leaving group, and we'd be stuck with our starting material right now. Now, I'm just giving you guys background information. Of course, you don't need to know this, but this is why this proton transfer step is not a plausible step in this reaction. The most plausible step in this reaction is doing a proton transfer step on this hydrogen and the carbonyl located on the peroxy acid. If we do this step, it would lead to an oxyanion that's attached and this will lead this with a plus charge. Now, we've narrowed down our sites of chemistry. Obviously, we need to get rid of this negative charge. So we would push electrons from the negative charge onto the single bond, which would then formulate a carbonyl group. And then we would do something called a migration step. A migration step would push one of these sigma bonds onto the oxygen so that we would go and form an ester. However, we have two different possible sigma bonds that could undergo this migration step. In this reaction, the most substituted R group, so in our case this CH3 and this alkyl group, would be the one that favors the migration step. Because of this, this oxygen undergoes a migration step on this carbon, which would render this a leaving group. So, as our final product, we would have this as our final product, which is called an ester, which is just an oxygen directly conjugated to a carbonyl group. And we'd also be given this, which in lab would just transform to this. Thanks for watching.